So we can go from 10 to the plus 25 to 10 to the minus 35. Now where are we? Well, the size of a living cell is about 10 to the minus 5, which is halfway between the two. In mathematical terms, we say it's a geometric mean. We live in the middle between the larger scale in physics, which defines the region we will ultimately see, and the tinier scale, which is so tiny we can't even talk about space and time on smaller scales than that. So we're in the messy middle. And the astonishing thing about recent discoveries in physics is they tell us the universe is surprisingly simple and regular on the tiniest scale and on the hugest scale. It's only complicated in the middle. Now I want to show you, this is a little bit of recent research with my collaborator at the University of Toronto. This is us trying to calculate what happened in the first billionth of a second after the Big Bang. So the beginning of the movie, it loops around, but the beginning of the movie are these smooth waves filling space. This is the end. Let's wait for the beginning again. There, you see these smooth waves filling space. They look very benign. But as they evolve, you see they form shocks, sharp edges. And these shocks then collide, and they will generate all kinds of interesting effects. So this wasn't understood until very recently, and it's an example of how we are following our knowledge back further and further into the deep past of the Big Bang. This is probing energies beyond the Large Hadron, what the Large Hadron Collider can do, but of course only theoretically. So now we know we have waves, but we know they're a bit weird. They come in these quanta. They can only carry energy in packets, determined by their wavelength. And how do we model the atom? Okay, so Niels Bohr was trying to think about the atom. The atom didn't make any sense from a classical point of view because the electron, which is orbiting the nucleus, would emit radiation and spiral inwards and into the center of the nucleus in no time at all, if classical physics was valid. You had to stop that happening, just like we had to stop the sun losing all its energy into tiny wavelengths of light. So the one thing you know about waves is they have standing waves. You can have standing waves. So you have some waves in a box, and the wave just oscillates like this, like a rope held at two ends. And so it can either have one, well, actually half a wavelength in the box, or one wavelength, or 1.5. So the number of these zeros of the waves, here we have 1, 2, 3, 4, 5, 6. So that's the sixth mode in the box. We can have the first mode, the second mode, the third mode, and so on. So waves naturally come in these discrete modes. If they're quantized, they can only carry energy in fixed packets. So this is what Niels Bohr did. He imagined the hydrogen atom. Here's the nucleus. And these are the electron, the possible waves the electron can follow. The electron goes round the nucleus. But when it goes round, it can go round in a certain number of wavelengths. In the circle inside, it goes round in 1 wavelength. In this one, it's going round in 2 wavelengths, 3 wavelengths, 4 wavelengths. And these, he conjectured, were the energy levels of the hydrogen atom. He didn't quite formulate it this way because people didn't know that electrons were waves at the time, so he did it in a more ad hoc way. He quantized the angular momentum of the electron, but it amounts to the same thing. So this was the model of the atom, spectacularly successful, but not really understood until people understood how an electron can be both a particle and a wave at the same time. So the wave properties are crucial to understanding the structure of atoms.